Very good morning, my dear students. Today we can calculate the SNR as well as the transfer function for optimum receiver. In the last class, we have already calculated the probability of error for optimum receiver. So, have we considered we completed, and just we have to calculate the value of SNR as well as the transfer function for the optimum filter. Now I request any one of the student to please tell me what is the probability of error for general baseband signal receiver. Any one of the student kindly respond. What is the probability of error for general baseband signal receiver? Any one of you please tell me.
One by 2 ERFC root EB by N naught, ma'am.
1 by 2 ERFC of root EB by N naught.
N naught.
Okay. Can you tell me what is the output SNR for the same general baseband signal receiver?
2 EB by N naught.
2 EB by N naught. And already we discussed this derivation for probability of error for optimum signal receiver. Can you tell me what is the threshold value considered for getting optimum response, optimum SNR? What is the threshold value considered here? What is the optimum value of threshold considered for calculation of probability of error for optimum receiver?
X01 of t plus X02 of t by 2.
Can you tell me what is X01 of t?
It is the output, ma'am.
Output signal. Very good. And when
input X of t is equal to X1 of t.
That is whenever input is at positive magnitude plus A, we consider it as plus A. And what is X02 of t?
When input is negative magnitude.
When input is of negative magnitude, we consider the output as X02 of t. Now what is N0 of t? N0 of t.
Noise.
Which noise? Output noise. Okay.
Yes.
What is N of t? N of t is the noise added in the channel. Okay. And N0 of t is the output at the output noise at the receiver section, because we considered R of t as X01 of t plus N0 of t when input X of t is at positive magnitude, and when input is at negative magnitude, we considered R of t as X02 of t plus N0 of t. Under noise free environment, we considered N0 of t as 0. So directly whenever N0 of t is 0, like whenever there is no noise at all, then we can directly attain the output signal as directly the output signal due to the corresponding input. The corresponding input may be of positive magnitude and negative magnitude. Can you tell me what is the expression we obtained for probability of error for optimum receiver?
One by 2 ERFC of X01 of t minus X02 of t by 2 root sigma.
2 root 2 sigma. Okay, very good. Thank you, thank you. Okay, here how we calculated, actually we considered the threshold as the ratio, the average of two output signals. The average of two output signals. That is X01 of t. This is whenever the input is at positive magnitude, and X02 of t is the output signal whenever input is at negative magnitude. Okay, here we considered input as positive magnitude. Then we know that R of t will be X01 of t plus N0 of t. Here error will occur when R of t is less than or equal to threshold value. That is whenever probability of error is less than or equal to threshold. We substituted the threshold value here and directly we got the value for n naught of t, the noise. Okay, we can evaluate or we can estimate. We can estimate because here noise is the unknown parameter. So we can estimate the noise by using the output signal components. That is, finally we obtained it as x, it is less than or equal to. Why less than or equal to? Because whenever input is at positive magnitude, output should also be positive. But whenever output is negative, whenever output is like less than or equal to the threshold value, then we can say that the corresponding noise component, the component is nothing but the error. So that's why we defined n naught of t as less than or equal to the threshold minus take this x naught 1 of t towards right hand side. So that we will get the, this is we defined as the lower threshold boundary. Okay, this we considered as lower decision boundary because within the graph distribution function of n naught of t, we defined it as fx of n naught. We have two decision boundaries, okay, constructed based on the threshold value. So one is n naught of t if it is less than or equal to x naught 2 minus x naught 2 of t minus x naught 1 of t divided by 2. We can get error whenever x of t is at plus a volts. And similarly, we defined whenever x of t is equal to minus a volts, that is whenever x of t is at negative magnitude, output should be always negative. But if our output r of t, if it is greater than or equal to threshold value, then we can say that there exists some error. That's why here p suffix e represents the probability of error. Here the probability of error will occur whenever like our output signal is greater than or equal to the threshold value. Here we assumed the threshold value as the average of two output signal components. So the average value minus x naught 2 of t. So that you can get it as x naught 1 of t minus x naught 2 of t divided by 2. So I can say that this is a upper threshold boundary or upper decision boundary. So using the threshold value, which is the average of the two output signal components, we have constructed two threshold boundaries for the noise component, for the noise. Here noise, we are estimating the output noise component. So that's why x axis is n naught of t and y axis is fx of n naught. So what are the two decision boundaries we what are the two decision boundaries we constructed? One is x naught 2 of t minus x naught 1 of t divided by 2, and another one, this is whenever input is at positive magnitude. And another decision boundary is x naught 1 of t minus x naught 2 of t divided by 2. This is whenever input is at negative magnitude. See, simultaneously you can observe the equations 1 and 2 and you can observe the graph. This graph represents the like probability distribution function of the output noise, because we are going to estimate the value of output noise. And please observe the equation 1. Here the equation 1 represents p suffix e of if n naught of t is less than or equal to the threshold boundary. What is the threshold boundary? Lower threshold boundary, that is x naught 2 of t minus x naught 1 of t divided by 2, same value. That's why we represented it here with crossed lines. Here these crossed lines represents the error or the noise obtained whenever or occurred whenever input is at positive magnitude. This is only the possibility. And whenever input is at negative magnitude, here also you will get error. That noise we defined it as probability of error. N naught of t, if it is greater than or equal to x naught 1 of t, same value we mentioned here, x naught 1 of t minus x naught 2 of t divided by 2. So these are the two threshold values. So this second threshold value this is noise, this kind of noise exists whenever x of t is at negative magnitude. Please always keep it in mind that whenever the noise crosses these two boundaries, wherever the noise is within the limit, then you can reduce the probability of error in order to increase the SNR. Okay, but whenever this noise crosses these two boundaries, this is lower boundary and this one is upper boundary. Whenever our noise crosses these two boundaries, we can say that there exists some error. So because of this error, our SNR will get affected. Okay. So here Gaussian distribution function with mean 0, already we defined it as fx of n naught of t. Here actually fx of the corresponding signal, but here we are estimating the noise. So fx of n naught of t is equal to 1 by sigma root 2 pi. This is root of 2 pi into e power minus of x minus m. Here m is 0, so that's why directly we represented x. X is the signal itself, that is noise component. So n naught of t minus m actually will get, but m is 0, mean is 0. So that's why directly I represented like minus of n naught of t whole square divided by 2 sigma square, where sigma square is the variance and sigma is the standard deviation. And we started the calculation of Gaussian distribution. So we used the same Gaussian distribution with mean 0. So directly the same expression I represented. And here we are going to calculate the probability of error when x of t is at minus a volts. Whenever x of t is at minus a volts, we said that the probability of error will occur whenever our noise component is greater than or equal to the upper threshold boundary, that is x01 of t minus x02 of t divided by 2. So that's why we took integration, and then this will be our this upper boundary will be our lower limit. Okay, so that's why we represented the same upper boundary value as the lower limit, and this limit extends to infinite fx of n naught of t into dn naught of t. Okay, so directly I substituted the value of fx of n naught of t in the probability of error expression. Then we can, if you directly substitute, it will be 1 by sigma root 2 pi into e power minus of n naught of t whole square divided by 2 sigma square into dn naught of t. What we did here, just we assumed the value of n naught of t whole square divided by 2 sigma square as some y square, because our intention is to represent this in the form of complementary error function, where the complementary error function is in the form of 2 by root pi integral u to infinite e power minus y square dy. Then you can represent that complementary error function as ERFC of u. Okay, so that's why we assumed the power value as y square. So you can see that the same thing here. So we assumed y square as n naught of t whole square divided by 2 sigma square. That is, what is y here actually? N naught of t divided by sigma root 2. N naught of t divided by sigma root 2. What is n naught of t? Actually, that is the output estimated noise. So we are going to replace dn naught of t in terms of dy. So that's why we directly represented like dn naught of t as sigma root 2 of dy. Sigma root 2 of dy. Now please change the limits. Whenever the upper limit n naught of t is infinite, then our y will also be infinite, because we are replacing the expression in the form of y. So dn naught of t will be sigma root 2 y, and whenever n naught of t, that is the output signal, if the upper limit is infinite, then y is also infinite. Whenever n naught of t, that is the lower limit, is equal to x01 of t minus x02 of t divided by 2, then from this expression we can say that y will be x01 of t minus x02 of t divided by 2 root 2 sigma. Just I have represented in the form of y, because y is n naught of t divided by sigma root 2. Directly I substituted n of t here, divided by sigma root 2 you will get. So that's why I mentioned like 2 root 2 sigma directly. Now upon replacing the limits and the expression in the form of y, directly you can define the corresponding probability of error whenever n naught of t is greater than or equal to the upper decision boundary. So what is the upper decision boundary here? x01 of t minus x02 of t divided by 2. Then it is integral the same lower boundary will be y, that is x naught 1 of t minus x naught 2 of t divided by 2 root 2 sigma, and upper limit will be infinite. So you will get it as 1 by sigma root 2 pi sigma root 2 pi into e power minus y square into sigma root 2 dy, because we replace dn naught of t as sigma root 2 dy. Now here if you observe the equation carefully, here sigma root 2, here you have sigma root 2 in the numerator and sigma root 2 in the denominator. Here these two gets cancelled, these two gets cancelled, so that your expression, you can represent the corresponding expression in the form of complementary error function. What is complementary error function? It shows the inverse relationship. Okay, it shows the inverse relationship, like whenever in the form of ERFC of u, which is equal to 2 by root pi integral u to infinite e power minus y square dy. So directly what we did here, here we represented the probability of expression in the form of ERFC of u. So directly here sigma root 2 gets cancelled and you will get 1 by pi here. Okay, and to get 2 by root pi as stated in the complementary error function, you can write it as 1 by 2 ERFC of x naught 1 of t minus x naught 2 of t divided by 2 root 2 sigma. This factor is nothing but the lower limit. So directly we represented the lower limit here. Okay. So now similarly you can calculate the probability of error expression using the same complementary error function whenever the probability of error n naught of t is less than or equal to the lower decision boundary. What is the lower decision boundary? X naught 2 of t, x naught 2 of t minus x naught 1 of t divided by 2. This is our lower decision boundary. If it is, then also you will get as half ERFC of x naught 1 of t minus x naught 2 of t divided by 2 root 2 sigma. So I think up to this we completed in the last class. So maybe few members were absent in the last class, that's why I revised here. So what is the probability of error expression here? Here just we took the lower limit as minus infinite and upper limit will be x naught 2 of t minus x naught 1 of t divided by 2. So just we interchange the limits. Okay, like you will take minus infinity to upper side and x naught 2 of t minus x naught 1 of t divided by 2 in the lower side, and we took negative sign as outside, so that negative gets cancelled and you will directly get the same probability of error expression. Okay, so please always remember what is the probability of error expression for optimum filter receiver. It is equal to half ERFC of x naught 1 of t minus x naught 2 of t divided by 2 root 2 sigma. Okay. Now what is x naught of t? What is x naught of t? Here x naught of t is the change in the output signal levels. That is x naught 1 of t minus x naught 2 of t. This is the change in the output signal level, because we represented x with the signal and x naught is the output signal. So x naught 1 minus x naught 2 of t as change in the output signal, let it be equal to x naught of t. And please carefully observe the denominator part. In the denominator you have 2 root 2 sigma. What is sigma actually? Sigma is the change in the output noise level. Sigma is the change in the output noise level and numerator is the change in the output signal level. That's why we can say that in the ERFC function we have one component which is defined as output SNR. That's why we are every time focusing on output SNR instead of overall SNR. See, general expression for SNR is defined as the ratio of output SNR to input SNR. But every time we are calculating the output SNR expression, because the probability of error is related to the output SNR. Okay, probability of error is related to output SNR as complementary error function of output SNR. Mean that as you increase the value of output SNR, you can reduce the probability of error. You can say that these two are like inverse relationship. Here the complementary error function gives you the inverse relationship as P of n naught of t is it is equal to half ERFC of x naught 1 of t minus x naught 2 of t divided by 2 root 2 sigma. So that's why we can conclude that as the output SNR, that is x naught 1 of x naught of t, because that is the change in the output signal, divided by sigma. Sigma is the change in the output noise level. Okay, as the output SNR in the complementary function increases, the as the here some like as there is an increase in the output SNR, the probability of error will reduce. Anyhow, I will modify the expression. Okay, not expression, like the statement, there is something wrong in that, but you should know that there exists an inverse relationship between probability of error and output SNR. Okay, now let us calculate the output SNR for optimum filter. In the baseband signal receiver, okay, we obtain the output SNR as 2 EB by N naught. Let us see how much you will get in this optimum filter. Okay, so once again I have rewritten the same expression of probability of error here. What is PE? Probability of error for optimum filter we are defining. It is half ER. See, please listen that. Remember that we are defining the probability of error for both the cases. For both the cases, we will obtain the same expression. That is, whenever our noise N naught of t, if it is less than or equal to lower boundary, and even if it is greater than or equal to the higher boundary, because we stated two decision boundaries, whatever may be, the probability of error will remain constant at half ERFC of x naught 1 of t divided by x naught 2 of t divided by 2 root 2 sigma. Numerator is a change in the output signal and denominator is a change in the noise component, okay, output noise component, because sigma is the standard deviation. So how much our noise is deviated from the mean, 0 value. So that is nothing but sigma. So every time here we will focus on maximizing the square of output SNR, because once you maximize the square of this function x naught of t divided by sigma whole square, if you maximize this, automatically you can reduce the probability of error a lot. Okay, in order to reduce the probability of error to a maximum extent, we are increasing the we are maximizing the square of output SNR instead of output SNR. Okay, that's why we are defining it with a new parameter or with a new variable rho. What is rho here? Rho is the change in output SNR whole square, or it is nothing but the you are maximizing the square of output SNR. So in terms of mathematical expression, here we are defining rho as x naught of t by sigma whole square, where x naught of t is the change in the output signal and sigma is the standard deviation and sigma square will be our variance. Okay, then we can reduce the probability of error to a maximum extent. Now let us calculate the output SNR and then the transfer function for optimum filter. So what is the input to the optimum filter? Just speak about the signals. So x of t is the input signal and the corresponding output signal is x naught of t. See, here we are not specifying at particular instant. So general value is x naught of small t, where small t varies, and here we derived the expression for particular instant t is equal to capital T. Okay, so let the Fourier transform of input signal x of t be capital X of f, and similarly let the change in the output signal, that is x naught of at particular instant at capital T is equal to let the Fourier transform be capital X naught of f, capital X naught of f. So then we can see the like the filter response as filter transfer function h of f as ratio of output signal, that is x naught of t, divided by input signal, that is x of f. Okay, so in terms of frequency domain, in terms of frequency domain, if you want to state, the transfer function is defined as a ratio of output signal to that of input signal in frequency domain. That's why we can define h of f as x naught of f divided by x of f. That's why I have defined the output signal in frequency domain, that is x naught of f as h of f multiplied by x of f. Because in the time domain you will have a convolution relationship, the same is replaced as multiplication in frequency domain. Okay. Now we got capital X of f. What is capital X of f? Capital X naught of f. This is the output signal, output signal in frequency domain, in frequency domain. Let us assume at t is equal to t, let us calculate the inverse Fourier transform of output signal. What is the inverse Fourier transform of output signal? Small x naught of capital T, because capital T we are at particular instant. It is the general expression is integral minus infinite to plus infinite x naught of f into e power j omega t df. Because if Fourier transform you will get integral x of t, x naught of t e power minus j omega t dt వస్తుంది. We are calculating the inverse Fourier transform. So x naught of capital X naught of f e power plus j omega t df. Please replace the output signal value in frequency domain. Okay, it will be h of f into x of f. Just we replaced in terms of transfer function into e power j omega t df. Okay, now let us calculate the transfer function and output SNR. Okay, please remember this expression, inverse Fourier transform of output signal x naught of t as integral minus infinite to plus infinite h of f into x of f into e power plus j omega t df. Now, let us calculate the output SNR first, then we can directly get the transfer function. What is output SNR? Let us assume the power spectral density of output noise signal N naught of T be Sn naught of F. See, I am using the same expressions what we used in the case of general baseband signal receiver. There also we defined Sn naught of F as the power spectral density of output noise signal. Okay, let us define the variance first. What is variance? Expectation of n naught of t whole square minus mean square. Expectation of x square minus m square and represent చేస్తారు మీరు general గా. But here x is the function itself is nothing but the x, the variable. So that's why directly we represented n naught of t whole square minus mean square. But you know the mean value is 0. The mean value is 0 for the corresponding Gaussian distribution, for the assumed Gaussian distribution. So that's why variance will be directly the expectation value of n naught of t whole square. Expectation is nothing but the mean of the n naught of t whole square. That is nothing but the magnitude, average value. So integral minus infinite to plus infinite Sn naught of f df. You know that in the baseband signal receiver we defined the mean square value of the noise signal as the noise power. Okay, and it is equal to the integration of its power spectral density. Integration of its power spectral density. Okay, so that's why integral minus infinite to plus infinite Sn naught of f into df. Already you know what is Sn naught of f. What is Sn naught of f? Square of the transfer function multiplied by Sni of f df. Square of transfer function into Sni of f df. Please observe the equation of variance carefully. So it is integral minus infinite to plus infinite h square of f into Sni of f df. Remember that expression. Now, Schwarz inequality states that, okay, Schwarz inequality states that the square of integration of the product of any two functions, what is that? Square of integration of any product of any two functions. Okay, so here I took the two functions as theta 1 of x and theta 2 of x. Okay, please observe this equation carefully and write down this expression in your notebook. The square of integration of product of any two functions, whatever may be the domain may be either time domain or frequency domain. Okay, irrespective of the domain, whether it may be time domain or frequency domain, the square of integration of product of any two functions is always less than or equal to product of integration of squares of individual functions. Okay, product of integration of squares of individual functions. So what, please remember, whatever may be the domain, okay, it may be time domain or frequency domain. Schwarz inequality states that see, in objective questions I will ask this question, state Schwarz inequality. Okay, this inequality is used here in order to calculate the output SNR as well as the transfer function. What is Schwarz inequality? It states that the square of integration of product of any two functions in time domain or frequency domain is always less than or equal to the product of integration of squares of individual functions. Okay, squares of individual functions. Okay, so that's why what we are doing here, we are defining the two functions using our expressions. Okay, so that we can calculate the x naught of t by sigma whole square, that is output SNR, square of output SNR. Okay, because output SNR is x naught of t divided by sigma, because we are going to maximize the square of output SNR. So that's why x naught of t by sigma whole square, that we considered as rho. Okay, what is rho? That is the variable which represents the square of output SNR. Okay, now make use of this expression, you can evaluate, and prior that please assume the values of corresponding signals. Let theta 1 of x, okay, here we are specifying in frequency domain. Already I told you, you can use this Schwarz inequality in either in the time domain or frequency domain. Here we are using it in frequency domain. So theta 1 of f is equal to h of f into root SNI of f. What is theta 1 of f? We considered as h of f into SNI of f df. Okay, and theta 2 of f is x of f divided by SNI of f into e power j omega t, because in the denominator you need sigma square, that is integral minus infinite to plus infinite h square of f into SNI of f df. See, if you take theta 1 of f whole square denominator, if you take theta 1 of f whole square, you will get h square of f into square root gets cancelled here, and directly you will get the SNI of f. Okay, so in order to get theta 1 of variance in the denominator, because that's why we are taking theta 1 of f square in the denominator and the product of these two in the numerator. See, if you multiply these two, you will get h of f into x of f into e power j omega t. Already I told you that as the output signal. In the earlier slide, I told you to remember the output signal, the inverse Fourier transform of output signal. It is h of f into x of f into e power j omega t integration. So if you multiply theta 1, theta 2 in the numerator, you will get output signal. In the denominator, if you take theta 1 of f whole square, you will get sigma square. Okay, like that you can calculate the variance. So what is Schwarz inequality? Square of integration of any two functions in time domain or frequency domain is always less than or equal to their individual products. Okay, integration of squares of individual products. Okay, just we assumed theta 1 of f whole square should be equal to sigma square, and these product should be equal to x naught of t, what we discussed in the earlier slide. Okay, so once again I have written here Schwarz inequality, so that every time it is difficult to go to the back earlier slide. So just I have represented the Schwarz inequality here, integrate minus infinite to plus infinite, theta 1 of x into theta 2 of x dx whole square. It's always less than or equal to product of individual integration squares. Okay, so already we assumed these as like conditions, that is theta 1 of f is h of f into root Sni of f df. See, in order to remember this, I told you how to remember the expression for theta 1 of f. So that theta 1 of f whole square should be equal to sigma square. And how should you define theta 2 of f? So that theta 1 of f into theta 2 of f should be equal to our output signal. Okay, so now to reduce the probability of error, already we from the starting itself I am telling you, in order to reduce the probability of error, the square of the output SNR, rho should maximize. Okay, in order to reduce the probability of error, we should maximize the square of output signal, that is rho. Already you know what is rho, square of output signal. It should be x naught of t divided by sigma whole square. That is our square of output SNR. So it is equal to, we are defining it in terms of the two functions. Integral minus infinite to plus infinite. What is this numerator? Square of integration of product of two functions. What are the two functions? Theta 1 of f into theta 2 of f df divided by individual function, that is integral minus infinite to plus infinite, because you should get sigma square in the denominator. So that is theta 1 of f whole square. If you square this, you will get h square of f into Sni of f df, that is nothing but sigma square. So we have designed in such a way. So what is rho? Rho should be equal to this value, but from Schwarz inequality, the numerator value is always less than or equal to their individual products. Numerator value is always, that is the overall product, is always integration of the product of two functions square. It is always less than or equal to the product of individual squared functions. So that's why we represented like less than or equal to product of squares of individual functions, that is integral minus infinite to plus infinite theta 1 of f whole square df multiplied by integral minus infinite to plus infinite theta 2 of f whole square df. If you design like this, in numerator, in the numerator and denominator we have same term, that is integral minus infinite to plus infinite theta 1 of f whole square df. So these two gets cancelled here. So numerator and denominator we have like integration of theta 1 of f whole square. So the corresponding term will get cancelled, and finally you will get it as less than or equal to integral minus infinite to plus infinite theta 2 of f square df, theta 2 of f whole square df. Okay, now finally you got the square of output SNR as less than or equal to integral minus infinite to plus infinite theta 2 of f square df. Please remember this square of output SNR, because once you maximize the value of square of output SNR, you can reduce the probability of error. So upon simplifying the output SNR expression, and please substitute the value of theta 2 of t, theta 2 of f. Already you know what is theta 2 of f, whole square you need. Theta 2 of f is x of f divided by root Sni of f into e power j omega t. Now please square this term. What is this term? X of f whole square So you will get, please I substituted theta 2 of f in the expression of rho. Here rho is less than or equal to integral minus infinite to plus infinite x of f square divided by Sni of f under root whole square you will get. So root and square gets cancelled here and directly you will get input noise power spectral density, that is Sni of f into e power j omega t square df. Here what is the value of e power j omega t square? Any one of you? Magnitude. Any one of the
1 ma'am.
student, can you
1.
చెప్పండమ్మా? 1.
1
How
ma'am.
it is 1? How it is 1?
E power j theta equals to cos theta plus j sin theta, ma'am. Then magnitude equals to 1, ma'am.
So e power j omega t is very good. Cos theta plus
J
j
sin.
sin theta. If you square that magnitude I am speaking, so it will be cos square theta plus sin square theta. So you will get it as 1. Okay, thank you. So directly I substituted the value of e power j omega t square as 1 because as I said you, the magnitude of e power j omega t square will be 1. So please substitute the value of corresponding value in the square of output SNR so that you will get rho as less than or equal to integral minus infinite to plus infinite x of f square divided by Sni of f into df, that's all. So what is the value of rho here? Square of output SNR. Here you should maximize the square of output SNR value. Here you should maximize the square of output SNR in order to reduce the value of probability of error. Because we got the probability of error expression for optimum filter as half ERFC of x01 of t minus x02 of t divided by 2 root 2 sigma. Okay, so it is proportional to square of input signal and inversely proportional to the input noise power spectral density Sni of f. So what is the square of output SNR? Here we are not at all defining the output SNR as in the case of baseband signal receiver because we are focusing on square of output SNR. Okay, so here we are focusing on square of output SNR instead of output SNR as we discussed in the case of baseband signal receiver. Okay, the square of output SNR, if you observe this equation, it is always less than or equal to. Okay, so what is the maximum value? It is proportional to x of f square and it is inversely proportional to Sni of f. Please remember that Sni of f, here it is for the optimum filter you should observe the Gaussian response. But if you go for the matched filter, you will get directly by using this expression. For the matched filter, Sni of f value is n0 by 2. So you can directly substitute the value of Sni of f as n0 by 2 or eta by 2. Here in the digital communication we considered it as n0 by 2. So if you take it as n0 by 2, you can directly obtain the value of square of output SNR. Okay, I think now you can be able to calculate, you can directly tell me the value of output SNR for matched filter. For matched filter, noise is, will assume the noise as to be white. Okay, then Sni of f will be n0 by 2. So directly the square of output SNR will be less than or equal to x of f integral minus infinite to plus infinite x of f square divided by n0 by 2 into df. So directly we can get the value of square of output SNR because for the matched filter noise is assumed to be white in nature whose power spectral density is uniform and it is equal to n0 by 2. So directly we can tell, you can tell me the expression for output SNR, square of output SNR for matched filter. Okay, let us move to the next slide. Next, I told you that we can calculate the transfer function for the optimum filter used. Here I told you Schwarz inequality and this inequality is valid only when theta 1 of f, that is the first function, is equal to some constant k times that of conjugate or complex conjugate of theta 2 of f. When so our Schwarz inequality, it is valid because we have calculated the output SNR using Schwarz inequality. Okay, and it is this inequality is valid only when theta 1 of f is k times that of theta 2 star of f. Here star represents the conjugate, complex conjugate. Okay, so what is theta 1 of f? H of f into root SNI of f. What is theta 2 of f? X of f divided by root SNI of f into e power plus j omega t. Okay, but here here what is the star we represented, that represents the complex conjugate. So that's why directly I represented the equation, but in the case of theta 2 of f, if you take complex conjugate, you can directly represent it as x of minus f, and e power plus j omega t you will have, you can represent directly it as e power minus j omega t. Okay, and here we did not represent anything for the noise because we assumed the noise to be white and Gaussian. So irrespective of the frequencies, our SNI of f is always constant at n0 by 2. Okay, so that's why we have changed, we have represented the complex conjugate value, complex values only to our signal and e power exponential term. Okay, because this is also a signal component. That's why we represented only the complex values only to the signal component. Okay, now what is transfer function? H of f, which is the ratio of output signal to input signal in frequency domain. So therefore our transfer function H of f of the optimum filter will be k into x of minus f divided by, please take this root SNI of f towards the right hand side. So root SNI of f multiplied by root SNI of f, it will be directly SNI of f, okay, into e power minus j omega t. So what is the transfer function of optimum filter? K is a constant. Okay, for a particular application k will be like given by the designer itself, k into x of minus f divided by SNI of f into e power minus j omega t. See, wherever I represented with rectangular boxes, please remember, you should remember those expressions. This is transfer function, and similarly square of output SNR, probability of error for optimum filter. Okay, with this we can conclude our module. Okay, so in this module we have discussed the probability of error calculation, transfer function, and output SNR calculation for optimum filter receiver. So any doubts in this module? In the next class we can continue with matched filter receiver. There we can calculate the probability of error for matched filter. So then we can directly jump to probability of error calculations for ASK, FSK and PSK. Okay. So you, from this it's very easy, and this unit is like very easy because so everything will go through the mathematical analysis. So if you remember like few points, you can easily attempt question from this. And one more thing is, you can score good marks from this unit. Directly you need to derive expressions. That's all. So can any one of you tell me the expressions for optimum receiver? Tell me the expression for probability of error, output SNR and transfer function. Any one of you. Can any one of you tell me what is the probability of error expression for optimum filter receiver? Any student please respond. Tell me the probability of error expression for optimum filter receiver.
1 by 2 RFC of x01 of t minus x02 of t by 2 root 2 sigma.
Okay, very good. Can you tell me the expression for output SNR? We calculated output SNR. Can you remember? Or you can see from the slide.
Integration minus infinity to infinity modulus of x of f whole square by Sni of f into df.
What is Sni of f? Input signal power spectral density. Power spectral density of input noise signal. Input noise signal is n of t. Its frequency domain is Sni of f. Okay. And can you tell me what is Schwarz inequality? Ma cheptara? Can you tell me Schwarz inequality?
Yes, ma'am. Integration minus infinity to infinity theta 1 of x into theta 2 of x into dx whole square is less than or equal to integration minus infinity to infinity modulus of theta 1 of x whole square into dx into integration of minus infinity to infinity modulus of theta 2 of x whole square into dx.
Okay, very good. When this Schwarz inequality is valid only when theta 1 of f is equal to k times that of theta 2 star of f, that is complex conjugate of the second function. So can you tell me the transfer function for optimum filter? Just read this expression, that is enough.
H of f is equal to k into x of minus f by Sni of f into e power minus j omega t.
Okay, thank you. And okay, please remember all these expressions, because in the exams directly you may get it as an objective question. So at least you should remember what you will get in the numerator and what you will get in the denominator. Okay. So in the next class we can calculate the probability of error. Similarly, the square of output SNR, everything in the for the matched filter. Okay. Okay. Now you can disperse. I took the attendance. You can disperse.